Hi, well, I'm Asmat. This is Aiden. Today we'll be talking about RedactedGPT. So redaction is the removal of sensitive information from private records. The goal of this project is to use transformer models to predict redacted text from declassified government documents about the 9/11 attacks. And why we want to do this, we want to demonstrate the level of protection redaction offers against LLMs. So the slight caveat is that we will not be working directly with redacted text. Instead, we will simulate the masking directly. The reason is that we need a lot of context to actually predict redacted text regions, which we do not have the compute resources nor the level of models for. So this is our data processing pipeline. There are two sources of data. The first data source are scanned PDF files from the CIA archive. The other one is a publicly accessible 9/11 Commission report. So these PDF files were converted to PNG files. The PNG files were then converted to text files, and then these text files were merged into a master text file. So some problems with the master text file is it's like these messy PDFs would some break the pipeline in the sense that there would be some unknown characters that would be in the messy PDF in the master text file, which we had to manually clean. So the masking process is as follows. So the first step is to select domain-specific keywords that are relevant to the context as well as had high frequency counts. For example, as you can probably imagine, bin Laden and Al-Qaeda are very relevant keywords for 9/11. The next step is to extract lines of text that contain these keywords. So the word before, the keyword, and the word after are candidates for masking. So for example, on the slide, you can see that CIA is the keyword, C is the word before, and report is the word after. Note that the explicit keywords were added to the tokenizer vocabulary. The next step is to only add mask candidates that are part of the tokenizer vocabulary. For example, as you can see on the slide, C and CIA are part of the tokenizer vocabulary, so they were added, but report wasn't, so it's not added. And the reason for this is that we want to reduce the number of embeddings which we have to train from scratch. So here are some statistics. There are 16K examples for each of the model data sets, as well as the trained test split is around 15 to 15. So the models that we use are from Hugging Face transformers, as well as we use Google Colab Pro for higher RAM and GPU compute resources. Our baseline model is GPT-2, which is autoregressive, and our models are actually bidirectional. So essentially, we want to test that bidirectional models are better than autoregressive models for this task because it has access to both the context before and after. So the difference between, so our models that we use are BERT and DeBerta. The difference between the two is that DeBerta is an improved version where it used two embeddings for the token, essentially to encode the content and the position. So training issues that we encountered was frequent GPU RAM overflow. And the two steps that we took to mitigate this was we had to move the evaluation to the CPU RAM, as well as what we had to do was to prevent gradient accumulation from the GPU, from the evaluation. So these are the hyperparameters we had to set. And essentially, it would move the evaluation to the GPU.
To measure our accuracy, use top K with K as 10. So just at the bottom, it demonstrates what that is, but we all learned this in the course. So we just did this to account for various decoding schemes and possible ways to generate like many tokens. So with hyperparameter tuning, these are the accuracies we could get. The highlighted ones are the best. We can see that DeBerta and BERT outperform GPT-2, and BERT is slightly better, which makes sense because it's a bit bigger of a model. And then just have some loss curves here. I'll just kind of go right through these. There's some overfitting there, but the accuracy is still pretty good. And then as a result, we have some examples which kind of demonstrate why we think these models perform differently. So GPT, basically, the core takeaway from this slide is the last example. It doesn't have access to Qaeda after the mask, so it doesn't know that Al should come before. So it'll get all those kind of examples wrong. But the top two examples demonstrate that it can get it right when it has the correct context. And then BERT does pretty well on both the top example, which is like a new token, and the second example, which is a token that's already in the model. It's just these infrequently used tokens like at the bottom that it gets wrong. And then DeBerta, kind of same thing, but kind of struggled with some commonly used existing tokens like among at the bottom. So then what we kind of showed with this, based on our accuracy in those examples, is that the bidirectional models do a lot better, as we expected. If we had a really large model, we think we could actually predict redacted text, but that requires too much context and too much computing power. And then also the initial keywords we chose to chain around are really important. So yeah, transformer models are not really memory efficient for tasks with a lot of training of brand new tokens from scratch. That's one thing we took away. So there's a lot of messing around with the compute resources to manage GPU, RAM overflow, things like that. Also, cleaning the data is difficult and iterative, and there's a lot of issues that can come up, especially when there's handwritten things over top of PDFs like we had. So to deal with this, we probably scope the project down. So we start with a gentle, small scope and gently scale up, and then try to find cleaner data sources, automate the pipeline, test it with some known results, and then try to work toward actually predicting redacted text from declassified documents. Get a lot more context, a lot more computing power. Just at the end, yes, okay.
Thank you.